Today's automotive engines, whether petrol or diesel, contain anything like 200 separate moving parts. They're made to sustain heavy loads, periods, and we expect them to go on working year in, year out, in all conditions. How well they succeed depends ultimately on good lubrication, on the complex blend of ingredients that goes into the making of a modern, high-quality engine oil. Oil is the lifeblood of an engine. It allows the working surfaces to move freely. But that's far from all it does. It has to work in a hostile environment. Heat, pressure, and the products of combustion all threaten to reduce its lubricating efficiency. How well an oil withstands such adverse conditions depends, in the first place, on the choice of a suitable base. The main source of automotive lubricants is mineral oils distilled from crude petroleum. They are readily available and offer the wide range of properties that are needed. Slightly alkaline, not too volatile, and with most of its wax removed, the suitability of a base oil is determined largely by its viscosity, its rate of flow. At low temperatures, for instance, some oils become too sluggish. Others, when they're hot, run too thin. What's needed is a selection of oils from which a base lubricant can be blended that will function equally well at different temperatures. Thin enough to give easy starting in cold weather. At the same time, thick enough to maintain good lubrication when running hot. A vitally important part of the oil's job is to absorb heat and carry it away from the working parts. So, from the sump, the oil is pumped to every part of the engine. Splashed round the timing gear. Delivered through jets onto cams and followers to flow over the valve train. Squirted into piston undergrounds to splash around gudgeon pins and onto cylinder walls. And through oilways in the crankshaft to reach the main and big end bearings. Without this continuous and liberal supply of oil, the moving parts would overheat, wear, and seize up. Take a closer look at a typical working surface. Under the electron microscope, it shows up as a series of jagged peaks and valleys. It's the oil's job to keep metal surfaces like these from touching each other. If the film of oil between them gets too thin, the peaks will rub against each other, weld, and tear apart. Paradoxically, this kind of wear is more likely to happen at slow speeds than fast. This model shows why. A moving belt and a plate floating close above it are kept apart by a film of oil. As the speed increases, the oil is drawn into the space between them, forcing them further apart. The tubes register the pressure exerted by the oil. The higher the speed, the greater the pressure, and the thicker the film of oil. When the speed drops, the pressure falls and the oil film gets thinner. But if a load is now applied, it forces oil out from between the working surfaces. The gap between them narrows, to the point where the oil film may actually rupture. This becomes critical whenever speed is low and the load is relatively high, as for instance in stopping and starting. It occurs in the eccentric loading on the crankshaft bearings, in the hammer blow delivered to a piston at its moment of rest, or in the pressure of a cam working against a stiffly sprung follower. Repeated rupturing of the oil film results in progressively serious damage and eventual failure. No base oil by itself can prevent this kind of wear. It's dealt with by improving the viscosity range of the lubricant. Greatly magnified, a mineral oil can be represented as countless individual molecules in constant motion. The hotter the oil, the more agitated the molecules become, and the oil gets thinner. To control this, a chemical additive is introduced. It consists of a complex molecule that expands with heat and restricts the movement of the smaller oil molecules. On cooling, it returns to its original size. So the oil maintains a consistent viscosity over a wide temperature range, the familiar property of a multigrade. Improving viscosity helps the oil to withstand some of the loads on working parts, but it doesn't go far enough. In many of today's engines, loads and speeds can be extremely high, where, for instance, the gearbox is built in. Imagine the gear teeth as a set of powerful nutcrackers. They can literally shear the oil molecules apart. Viscosity breaks down, and the oil is thrown out, exposing the metal surfaces to overheating and catastrophic damage. To enable the lubricant to cope, a different kind of additive is used. It consists of molecules which bond chemically with the metal under intense frictional heat. They form a protective layer, allowing the surfaces to slide over each other without damage. While some additives enhance the lubricating properties of the oil, others are needed to protect the oil itself from the hostile environment of the engine. An engine is like a giant egg whisk, mixing air intimately with the oil. Too much foam reduces lubricating efficiency. It's controlled by an anti-foaming agent. But it's the presence of oxygen whisked into the body of the oil that does the real harm. As the oil heats up, it oxidizes and thickens. The hotter the oil, the more readily it oxidizes. Left unchecked, carbon builds up on the valves and piston crowns. This can lead to pre-ignition or to knocking. To arrest the oxidation process, another additive is introduced. It renders the oxygen molecules inactive. This keeps valves and piston crowns free of carbon, but the high temperatures and pressures around the piston skirt produce a further problem: lacquering. Gummy deposits of half-burnt fuel and oil cause the rings to stick, leading to piston wear and loss of power. To stop this happening, a detergent additive is used. It won't make a dirty engine clean, but it does form a protective barrier on metal surfaces and prevents gummy deposits from sticking to them. It keeps the metal clean, but at the expense of contaminating the oil. In any engine, complete combustion of the fuel is rare, and this causes problems, particularly in diesels. Under high compression, half-burnt gases, fuel and particles of carbon are blown past the pistons into the oil. By themselves, the carbon particles are far too small to do any harm. It takes 3 million of them to cover a pinhead. In the cooler parts of the engine, however, they tend to join together with water, resins and acids and settle as a thick sludge, obstructing oilways and clogging filters. A dispersant additive prevents this. A film of insoluble chemical forms around each particle, keeping them separate and small enough to pass easily through the oil filter and between the working parts. Even when an engine stops, the oil is still open to attack. As the metal surface is cool, water droplets form. Water encourages rust. It also combines with sulfur and hydrogen compounds to produce highly corrosive acids in the oil. The alkalinity of the base oil neutralizes some of the acids. But further protection is given by an anti-corrosion additive which coats the metal surfaces with an impermeable layer. No oil can last forever. Cooling, cleaning and protecting, its components are gradually used up and have to be replenished. What matters is how well they've done their job. Oils, like the engines they serve, are constantly developing and changing. The more efficient and powerful engines become, the more stringent the demands they make on the oil. Engines also vary considerably in their design, whether petrol or diesel, air-cooled or rotary. Each has its own particular lubrication needs. They can only be met by studying the effects on engine performance of each of the oil's components in turn. Tests are needed to ensure that the base oils used are chemically stable and have the necessary range of properties, and to assess the precise effect of various additives in improving flow, increasing resistance to wear, and preventing corrosion. But the real skill comes not just in selecting the best components, but in achieving a delicate balance between them, so that each can make its optimum contribution without interfering chemically with the performance of any other, and so remain fully effective from one oil change to the next. The result is a range of high-quality engine oils that can be trusted to do their job, whatever your engine, and however extreme the conditions under which it has to work.